Yeah. So in the last class we started off with conduction, convection, and radiation as the three processes of energy transfer from one place to another place. So we have conduction, convection, and radiation. Now, the process of conduction is when molecules actually transfer the energy from neighbor to neighbor. Convection is when heat energy is transported from one part of a fluid to another part of the fluid in a bulk manner. There's a bulk flow, mostly due to expansion. And radiation is something that goes at the speed of light, and it does not need a medium to travel. So radiation does not require a medium. Any hot object will radiate. Okay? So conduction, convection, radiation. As is again, conduction is a process by which atoms transfer the energy from one to the other. Now, if I take a block of something, if I take a block of some material, and if I keep this side at a higher temperature and the other side at a lower temperature, so I'm going to keep this side at a higher temperature, let's say T2. And on this side, I keep a lower temperature, T1. Like say 100, 0, or something like that. Okay? So if I keep different temperatures on different sides, what's going to happen is this side, because this is highly agitated, the atoms over here will get agitated and they'll pass on the energy to the neighbor, and they pass the energy. Finally, the energy will be going into this section here. Now the rate of heat flow, the rate at which heat flows, the rate of flow of heat, dq over dt or delta q over delta t, is proportional to what? What are the factors? How fast is energy going to be transported depends on what factors. What do you think, so? Like, it's a block.
What kind of material?
What kind of material? Yep. It depends on the material. Also proportional.
Area? Volume?
Do you think it's directly or inversely? Area.
Inversely.
Which means if the area is bigger, less heat will go through. And if the area is like a fine wire, more heat will go through. Think of it. Like if I take a thin copper wire and put it into fire, one end is kept on fire, you'll get burnt very quickly. Or a thicker one, which will transfer more heat. A thicker one. If it's more area, more flow. The flow is dependent on the area, so the area is an important factor. So the area is an important factor. So proportional directly to the area. The more the area, the more flow, rate of flow. The rate of flow depends on area, it depends on the material. What else does it depend on? How fast the energy goes depends on what other factors? Any other factors that you see on the board? What other factors will this depend on? Like delta Q over delta T means the rate at which heat is going to flow through. The power of transfer of energy depends on, you said material, correct. You said area, directly proportional to area. That means if I have a broader material, it's going, in other words, if I have a bigger window, it's going to pass more heat. If I have a tiny window, it's going to pass less heat. You understand? Area is important, yes.
Distance.
The length, yeah, the length What do you think is it? Is it directly or inversely on this?
Inversely.
It is inversely proportional. Like if you have a long material, then the heat is going to be flowing at a slower rate compared to thin material. Like if I have a thin window, especially in the construction world, you know, you should be thinking about these things. Like if you have a thin window, do you think it is going to be efficient in reducing the rate of flow? Or a thick window? Of course, a thick window is going to be slowing down the process. A thin window is easy to pass through, right? So inversely proportional to length. So the longer this material is going to take a long time for the heat to go through. What else does it depend on? The rate at which heat flows from one point to the other in a material depends on what other factor.
Outside temperature? Like if it's
Look at the board and tell me.
what if it was like 10 degrees Celsius and you were trying to heat that, would it slow it down? Because it would be radiating that heat.
Where are you saying 10 degrees?
I'm just making it, yeah, I'm just like...
Okay, I mean, you're touching the point, but not exactly right
So
there.
the delta T.
Okay.
Just change
Temperature
T to 1.
difference. Yes. Like if this is at 100 degrees Celsius and this is also at 100 degrees Celsius, nothing's going to happen. So for heat to flow from one place to another place, you need temperature difference. If there's no temperature difference, why should heat flow? Right? The heat, like for example, this table, is the heat flowing on this table from here to here? No, because that side is also same temperature as this side. Why should there be any heat flow? So the heat will flow only if there is a temperature difference between one place and another place. Like for example, the window. If the outside temperature is 24 degrees Celsius, inside is also 24 degrees Celsius. Nothing is going to. Well, I won't say nothing is flowing, but it's flowing at equal rates. Whatever is happening from there to here is what's happening from here to there. So the flow is exactly equal. So the rate at which heat flows is also proportional to T2 minus T1, the temperature difference. It depends on. So putting all these things together, I'm going to raise this for the time being. Putting all these things together, you have delta Q over delta T, so the amount of energy that flows in a certain period of time. Okay, I'm not taking it as a small thing. Is proportional to area T2 minus T1 over L. And Q over T is equal to K A T2 minus T1 over L. And K is called K is the proportionality constant. And what is the proportionality constant called? Thermal. Sometimes they say thermal coefficient, thermal conductivity. K stands for thermal conductivity. Different materials have different thermal conductivities. Like how nicely heat can flow through depends on this K. So if you want it to be a good conductor, then K should be high. If you want it to be a bad conductor, then K should be low. So K is the thing that depends on the material. K is called thermal conductivity of the material. Okay? T2 minus T1 can be in Celsius or Kelvin because it's a matter of change in temperature. It doesn't matter. Area should be in meters squared. L should be in meters. Q over T is watts. So what's the unit of K? What's the unit of K? That is watts. Area over length is just meters over here. So watt per meter Watt, meter minus 1, Kelvin minus 1. You see it? This is watt, meter minus 1, Kelvin or Celsius minus 1. That's a unit of thermal conductivity. Thermal conductivities of different materials are different. And like for example, silver is 420, copper is 380, it conducts. Aluminum doesn't conduct that much, it's 200. Steel is only 40. So you can see if I have a copper spoon and if I have a steel spoon, the copper spoon will be almost 10 times faster in conduction. Okay, because copper is 380 and steel is 40. 40 watt per meter per Kelvin. Ice is 2. Ice is only 2. Doesn't conduct heat through it that well. That's the idea of the igloo, right? When you construct an igloo, which is what you can do in an icy place, and when you're inside, you can keep yourself warm. Although the wall is ice, it kind of locks the air inside and thereby kind of does not let your body heat to escape to the outside much. Okay? Ice is only 2. Glass is 0.84. Glass is only 0.84. Brick is also roughly 0.84. Concrete is also same thing. Water is 0.56. Look, water is a bad conductor. Water is a bad conductor. The very proof of that water is a bad conductor is through a simple experiment. Suppose you take a test tube. So you take a test tube. You put some ice at the bottom of the test tube and just stick it there with some metallic, what do you call that? Metallic wool, you know?
Steel wool.
Steel wool, yeah. Put that steel wool and like jam the ice down here. So that is ice. And this is a test tube and that's water. Now, heat here. Like put a burning candle right there. And what you'll see is this. This water starts boiling. This will be at 100 degrees Celsius. It will be boiling when this ice is still intact. The ice will still be intact. It's not melting. Why? Because, okay, this is boiling here because you supplied energy to that spot, but it is not going to, the heat is not going to go down here. Why? Because it's a bad conductor. Water is a bad conductor. It does not go that easily. The heat does not travel that easily through it. That's why the ice stays intact. Now, one of the reasons why we actually put the heat at the bottom of a container is that when you heat the bottom, the heat is passed on there, and conduction, you don't expect conduction in water. Convection is what is happening there. So what happens as soon as you heat the water expands. And when it expands, it becomes lighter. So it becomes buoyant. So it starts rising. When it starts rising, then the cooler water will get inside, get warmed. So it kind of starts circulating like this. Have you seen that circulation? That is convection. So convection is the way by which you're driving the heat everywhere in water. When you're supplying heat at the bottom of a container, that's convection. If you supply heat here, you have convectional currents like that. This is what you see in water. So if you see water kind of moving like that, that is purely convection. So how the heat that you supplied here is going to this point is not by conduction, but by convection. Conduction is very slow. So if I take water like that and put an immersion heater here like that, it will boil this water. You can see it boiling, but this part will be cool. Because cold water is heavier, so it will stay at the bottom. And this one is hot, so it will stay hot. No chance for this one to come out. or this heat to go down. So in a water heater, always the heater coils are kept at the bottom, so you'll actually have movement. Okay. So yes, so water is a bad conductor. Human tissue is 0.2. Human tissue is 0.2. Not good. Wood is 0.1. You can see how the conductivity changes. Fiberglass, the one which you use for drywalls and all that, inside, 0.048. Now, conductivity, thermal conductivity is an important thing in the construction world. Fiberglass is 0.048. Cork is close, 0.042. Wool is 0.040. You know, the woolen jackets and all that you wear, that one, this one. What is this called? Goose down, I think it's goose feathers. 0.025. Lower than wool. That's why they actually can trap a lot of heat. Polyurethane, 0.024. Air, 0.023. Air is the worst one. Air is a bad conductor. So if you can have air trapped, then that will be the worst conductor. Thermal conductivity of air is 0.023. That's a bad conductor. So now you should be able to answer, why are we kind of feeling comfortable when we dress in layers in winter? Why do we have to dress in layers? Why can't we just wear one cloth which is thick? Yeah.
The air between the layers.
The air between the layers. So when you wear one shirt, wear another shirt on top, wear another shirt on top, you're good. What happens is between the shirts, what is there is air trapped. And that air trapped is a bad conductor. And that makes this thermal conductivity of the whole combination pretty small. So you feel comfortable with, instead of one thick fabric, it won't do much. If it is one thick fabric, it conducts. It's like, imagine you take a leather jacket, just a leather jacket, and wear it. It's not going to be good. Whereas a leather jacket with some lining inside, that makes a difference. Because that lining is going to trap the birds. When they, in winter, you can see birds fluff their feathers out like this. Why? Because they want to trap air inside their feathers so that they can protect their body heat from going out. You understand? So the secret is air. Air is a bad conductor. Now glass is how much? Glass is 0.84 and air is 0.023. So if I have a glass window has a K that is big. So instead of having a glass which is 10 millimeters thick, if this is the glass window 10 millimeters thick, that is not going to do a good job. Why don't we just split it up? Make it 5 millimeters and a little gap and put the next 5 millimeters. So that is a window which is called double glazed. Like this is a 5 millimeter window glass, and this is a 5 millimeter glass, but separated by air, little air. Can you see that window closely? There's two glass panes on that. Look at the glass window closely, and you'll see two. It's not one. Most of you at home have the same thing. So if you see glass windows, especially in this country, you should have double glazed or triple glazed. I got my windows recently changed to triple. 3 glasses like this. So definitely this is far better in terms of reducing the heat flow than this. This is terrible. But just split it like this and makes it very good. So what is exactly happening here is if the outside is, let's say, if the outside is 0 degrees Celsius, 32 Fahrenheit, and the inside of the room is 25 Fahrenheit degrees Celsius. So inside is 25, outside is 0. You can see the rate at which heat flows is tremendous. Now, if the same thing happens here, it's 25 degrees Celsius and outside is 0 degrees Celsius, what happens is, because this is a fairly good conductor, the temperature on this side of the glass is roughly 24. And the temperature on this side of the glass here is like 1 degree Celsius. Now, between these two, there's a temperature of 23 degrees Celsius, but because it's a bad conductor, the heat flow from here to here will be terribly slow. It's very quick to go from here to here. It's very quick to go from here to here. But this part is a bad conductor. Now imagine if you have 3 panes, far better. That being said, since air is a bad conductor, why can't I do this? Five millimeters, and a big chunk of air. Which one is a better insulator? Which is a better insulator? Which is a better insulator? So this is air, glass, glass, air, glass, glass. Which is a better insulator? Which will stop heat flow better? This kind of window or that kind of window? Your ideas. Like you saw that window there. If I construct a window that is that thick with 5 millimeter glass and have a good amount of air inside, you increase the length. Area is the same thing, but you increase the length. Will it be better? Or yes.
Is there a problem with the expansion of the air when it's hot?
In which one?
The second one.
You mean expansion, overall expansion?
Yeah, but it's damaging.
It will expand. A little bit of expansion will be there, but the glass will be able to tolerate that expansion. Expansion will be there here also. Here is less air and less volume. It's more air, more volume. So if you look at it that way, it's the same. So whatever experience is going. So which window is better? Is my question. Go ahead, shoot for one of them.
The big one, because as length increases, it's inversely proportional to each other.
This one, as the length increases, it looks like, according to the equation, Q over T is equals to Ka temperature 2 minus temperature 1 over L. According to that equation, as L increases, it looks like the rate of flow should be reduced. Right? But this is better. Why is this better and why is this a terrible idea? Is because of the second of the methods of methods of transfer, convection. So what's going to happen here is this part of the glass is going to be 24 degrees Celsius. This part of the glass is 1 degree Celsius. So what is happening to the air inside here? Look, this is 24. So what will happen to this part of the air? Will start rising. So this part of the air will start rising like this. As soon as it's warmed up, it will rise. And this one is like going to sink. And so it will start circulating like that. So the moment you actually like expose this window to outside 25 and to 0, bulk movement of air from here to there will transport energy straight away. So it won't remain at 1. Very soon it will reach 24 because this heat is going straight there. You understand? Now what's happening in this one? Because it's so small, this one's rise and that one's fall is kind of clashing with each other. So it's not going to move. You're restricted the movement here. That's why it's very thin. So the thinner you have, the better. Okay? So in this, convection is not allowed. In this, you're allowing convection. So therefore, this is not a good idea. Now, okay, that's about the windows. What about your drywalls. In your house, you have a drywall here, and you have a drywall there on the outside, and the studs in between, right? What's inside? The insulation, the R13s, R9s, all those insulations. That insulation is sitting inside here, and that is a bad conductor, right? Which one is a better insulator, fiberglass or air? Fiberglass is 0.048, air is 0.023. Which is a better insulator?
Air.
Air is a better insulator. So what is between here is basically air, and what are you filling with? Fiberglass, which is a better conductor. You know what I'm saying? You understand what I'm trying to say? You have two drywalls, and inside here we have air, and that air is a bad conductor. And when you put this pink material, which is fiberglass, you're stuffing this place with fiberglass, and fiberglass is a better conductor. So what's the purpose of putting the fiberglass? What's the purpose then? Yeah.
Heating cost.
But then you're putting a better conductor.
This air can get in the material in between all
Fiberglass.
the
But then if you don't have the fiberglass, there's air everywhere.
It inhibits convection.
Huh?
Does it inhibit the convection?
The convectional part of it. That's why I gave you this idea just now. So what if you don't put fiberglass at all? Convection is going to take place inside. So from this drywall to the other drywall, energy goes straight away by convection. Whereas when you put this fiberglass material here, so you're putting this, like fiberglass inside here. So what is the fiberglass going to do? It's going to trap air, and of course it's trapping air, and not only trapping it, letting the air not move. It's kind of refusing the convection. So the fiberglass here prevents convection to a good degree, and that is the reason why this is better. You understand? So air is a bad conductor, but fiberglass is being put inside in place of air for the reason that you don't want flow. You don't want flow. Now, foam kind of insulation is also being used these days, which is polyurethane, which is 0.024. That's better than fiberglass. Have you seen that kind of insulation? Yeah, like it's just expanding foam. All you do is make a hole in this and just push it inside. It'll just fill up this entire place like a wall of fiber, a wall of polyurethane. And that will be better than fiberglass. The reason that is almost air. Because you see, polyurethane is 0.024, air is 0.023. Look at the difference. So, styrofoams, they are as good as air. The styrofoam insulations are as good as air. So if you have a box of styrofoam, you can put some cold stuff inside, and it'll keep it there. Yeah.
What if you just fill that space up with balloons?
Say it again.
You just fill up the whole space with a bunch of balloons. Would that be good?
Yeah. But how long are they going to last? How long are they going to last? That's a good idea. If you can have a bubble wrap.
Yeah.
Insulation.
Yeah, bubble wrap is basically, it will do it. In fact, if you make a jacket out of bubble wrap, it'll keep you warm. Really, seriously. No, seriously. If you can just come up with that bubble wrap thing,
It's the new truth.
well, don't expect people will kind of poke holes on it and try to pop it up, and no time it'll be all done, and it'll be just plastic sheets. Yeah, bubble wrap actually will do this. Even just a plastic cover over your body in winter will keep you pretty warm. Just throw a plastic cover on your body, it'll keep you warm. Because air cannot escape that easily because there's a lot of trapped air inside. Now, if you wear a shirt that is absolutely tightly fitting to your body, well, it is not going to do a job. Because if it is tight, it's going to leak it. But if it's loose fitting, it's better. So most of these things are not supposed to be tight. It's supposed to be loose because it's supposed to trap the air. Now, you see fiberglass here? Now suppose you put some fiberglass here and then you saw, oh, I've got many rolls of extra fiberglass. What do I do with this? Let me stuff it inside. So what you do is you stick more fiberglass inside here. Instead of one layer of fiberglass, you put many layers of fiberglass. Good idea, bad idea? Bad idea, because when you're stuffing more stuff there, you're turning it almost into glass. It's supposed to be fiberglass with holes of air inside. Now you're pushing all the air and trying to make it just glass. So if you just make it fully glass, it's bad. You get it? Brick walls. It says brick is 0.84. If the brick is 0.84, is this brick wall a good one? Yeah. Brick is 0.84. What is special about this brick that makes it a better insulator? It's hollow. It's hollow. It's not a solid brick. It is not a solid brick like complete chunk. You know, like in the garden you have solid bricks. This is not that. It is hollow. It's just like this. It's like that. It's like this. It's a hollow thing. So what is inside here is air, and you're piling it up like that. Yeah, it is not very strong like that, like normal bricks, but this is the main reason of the hollowness is reduce the material and increase the decrease the thermal conductivity. Yes.
Is the partition in the middle of the convection?
It also, yeah, it helps in convection. I think it's mostly there for strength. Yeah, mostly it's there for stability and strength, not for. It will also help in conventional part of it. But then you have these pockets. So each brick has two pockets, and so because they are in pocket formats, convection is not going to be that easy. It will be there, but it won't be that much. Now, in the construction world, we don't actually talk about thermal conductivity. Why? Like, I can't say thermal conductivity to the brick. The reason is the brick is not made of one material. It's made of brick and air, right? Where again, the wall. Is this wall one material? How many different materials are there in a wall? Drywall, the gypsum board. The gypsum board on this side. And then you have fiberglass wool. What else?
Wood.
The wood, and then the air. So when you want to write an expression for this, that equation Q over T is equal to A T2 minus T1 over L over K. And this whole thing is actually called the R value. R value. This is called the R value. So you can see what I've done here. I've just brought this K down under the L, and this whole quantity is called the R value. So Q over T is equal to A T2 minus T1 divided by R. So in the construction world, when you want to build something, they will say, all right, what is the R value of that brick? It's not thermal conductivity that you're concerned about, R value. Have you seen fiberglass?
Yeah.
Have you seen the labels?
Yeah.
Have you seen R13, R9?
Yeah.
That's the R value. So R value, so this R value, if it is big, that means it's going to be better. So if you're going to buy fiberglass insulation, and if you see R9 and then you see R13, well, R13 is better because that is going to stop heat flow better. So that's called the R value. So when you're looking at a composite material like this door is not fully wood. It's got a wood sheet in front, it's got a wooden frame, and it's got pocket of air, and then there's another wood sheet at the other side, right? So if I want to like find out something about conduction for this, I cannot look for thermal conductivity. I'll be looking at the R value. So how much is the R value for this door? How much is the R value for this false ceiling? How much is the R value for that double glazed glass? Because that is not fully glass, it's glass, air, glass. So R value is more looked into than the actual thermal conductivity K. Yes, you work with thermal conductivity only if it's one material. Otherwise, you can't use that equation. All right. Also, yes.
Are gases in general worse connectors?
Yeah. Because the atoms are far apart. That's one of the reasons why they become bad conductors. The more closely packed they are, the better conductor. That's why you can see on the conduction, on the thermal conductivity, silver is 420 because it's pretty nicely packed. Silver's density is higher. Copper is also highly packed. Aluminum is loosely packed, so it's almost half of copper. Steel is 40, but steel is 40. It is packed pretty well, but there are other reasons why steel has got only 40. Because the degree of movement, the freedom of movement of these atoms, that also makes a difference. Like, okay, there are atoms, but they're not free to move and pass the energy. So that makes a limit on it. Ice, the same thing. Water is 0.56, but ice is 2. So ice is better in conduction. Now, convection. Convection, is mass movement of fluid. So we're not going to do any calculations based on it. The basic idea is fluid, when it is heated, when a fluid is heated, the heated fluid expands and therefore has a chance of moving. And that movement is actually called convection. In fact, the air or the wind that you actually see outside is caused by convection. The wind is a result of convection. Why? Because one side of the region is hotter and another side is cooler, so expansion, and then the flow will start moving, the air will start moving on. You must have heard about sea breeze and land breeze. Sea breeze and land breeze. What is a sea breeze? Sea breeze obviously is like when you go to the beaches, you get nice cool air blowing on your face. That's called sea breeze. Okay? That's called sea breeze. Have you heard the land breeze? Never? Okay, sea breeze. Now this is sea. And that's land. That's the sea and that's land. So what happens during the daytime? That's when you go to the beaches, right? During the daytime, sunlight is hitting the land straight away. And because the land, the specific heat capacity of the sand is not too much, it heats up so fast. So sand becomes really hot compared to the water. So which one is hotter during the daytime? So land is hotter than the waters, right? So what happens is because this part is hotter, the air here will heat up. And when the air heats up, what will happen to it? It will rise. The air will start rising here. When the air starts rising, the cooler air from here will come in and replace it. And because the cooler air is coming from here, this heated air will start cycling like this. It will start cycling. So when you stand here on the land looking at the sea, what you are getting is this one, which is called the sea breeze. It's a breeze that comes from the sea. And what kind of temperatures is cool? Because it's running over the waters and it comes to you. So it's cool breeze. Even if it's a hot day, you go and stand next to the beach, you'll get nice cool breeze coming in. That's called sea breeze. What is land breeze? Land breeze is during the night time. During the night time, the land cools pretty rapidly. And so if you're going there in the middle of the night, the land is cooler than the water, because the water traps the heat during the daytime, and therefore because of its high specific heat capacity it holds on to that heat. So this part is warmer, and so it starts rising from here, and this one starts coming in, and so the land breeze comes like this. So if you go in the middle of the night and stand next to the beach, you can feel the breeze coming from behind you, pushing you into the water. Right? That is called land breeze, and it'll be very, like this won't be a pleasant breeze because it's like warm sort of thing. This one. Water is cooler, but this one is actually warmer. The air, the wind that you experience will be warmer. That's called land breeze. Now, where else is convection used? Fireplace. What's the purpose of fireplace? For what kind of transfer of heat? Radiation. The fireplace's main job is radiation. So when you turn the fireplace on, it pushes the heat out in the form of radiation. So immediately you can feel it. The heat will come immediately. But take a little while to find out what exactly is happening in a fireplace. So that's a fireplace. And you're sitting here. So the fire is burning. When this burns, what happens? What happens to the air? What happens to the burnt smoke and all those things? That is not what is heating up the room. You don't want that. And therefore we have the chimney. So the chimney will take it out. So what is happening is the fire burns and all this air and carbon dioxide and all those things is kicked out from here and out of the house. Now for the fire to burn, okay, so when the fire burns, you get radiation. But for this fire to burn, what is needed? Air, oxygen. So where is it coming from? From your room. The oxygen is actually coming from your room. So the air that you have to breathe is going in here and enabling the burning process. And after burning it, it is pushing it out from here and gone. So eventually what's going to happen? You're going to lose all the air. You'll be lacking in oxygen after some time. So what will happen if you lose oxygen? I mean, like if you have less oxygen, what will happen? The first symptom of lack of oxygen is yawning. You'll start yawning. You'll be sitting comfortably and you're getting the nice heat from the radiation, but after some time you'll start yawning. I can see some of you already doing that. The word yawn itself is like, alright, so yawning is the first thing. And if you don't get an idea of why are you yawning, I just had a sleep, and why am I yawning now? The reason is there is lack of oxygen and you're trying to intake as much as possible. That's the idea. And if you don't take care of that, what will happen is it will take the entire oxygen from your room. Because you are feeling sleepy, you'll sleep, and that will be the last sleep. Yeah. Because you sleep comfortably, and after that your brain slowly cuts off because oxygen is out, and slowly it puts you to sleep. So what is therefore to be done? If you're constructing a fireplace, you can't just do this. You have to have some ventilation in the room. You need to have ventilation like that. You need to have ventilation. Yes, this is exposed to the outside, and therefore can your room heat get lost? Yeah. But most importantly, you need air in. So you need fresh air to come in. It's a cool air that's coming in. But you know what? The cool air that comes in supplies you with fresh oxygen. And as soon as the air comes in, this radiation will heat it up. The radiation is going to heat up the air. And so you'll be fresh because you're getting fresh supply of oxygen from outside if you have this ventilation going on. So make sure in your fireplace room, make sure there is enough, there is a ventilation. If ventilation is not there, the danger is as I said, it will take out all the oxygen that you need to breathe, and therefore it will put you to sleep. Okay, so a fireplace is fine, but you need supply of oxygen into the room. And what happened many years ago, like over here in Louisville, when we had the ice storm? All right, when we had the ice storm, we lost electricity. Almost like 75% of Louisville lost electricity. There was no, people are, like going here and there. Generators were in hot sale. People were needing it. There was a family of 5, I think it's downtown. What they did was this. They sealed the entire house because it was cold outside. So in order to stop the heat from being lost from inside the house, they kind of sealed the house, made sure that there's not a single hole under the door, everywhere. Seal. And after they sealed it, well, they don't have electricity. And therefore, they cannot heat the room in any way. So what they did was this. They brought their barbecue grill into the room. So they set up the barbecue thing, and they just made their, hamburgers on it, and they had their last supper. They had their last supper, and then they all went to sleep. Yep. And then they all went to sleep. They were all in nice sleeping posture. What happened actually was this. They finished their, so for this barbecue thing to work, it was continuously, like heating up the room. And for that to work, it requires oxygen. So it stored their oxygen. That's why they're feeling sleepy afterwards. So they went to sleep. And what was this doing was it was taking out the good oxygen that they were supposed to get, and in return giving carbon monoxide and stuff. So it was a poisoning, and at the same time cutting off the oxygen. So all the 5 were seen dead. And there was no panic. Because if they panicked, they could storm out of the house, right?
Is this scenario with a closed door to the room, or is this?
They sealed the entire house.
Yeah. Like you should make sure that there is enough ventilation somewhere or the other. Yeah.
So is this similar to like a running car in the garage, like a closed garage?
Oh, exactly. Yeah. Yeah. Good point. Yeah. If you actually keep running the car in a closed garage, you enter the garage, you'll be like, you're losing your breath because you don't have oxygen. It's all carbon monoxide right there. So even if you like open the garage, we don't want to open the door because it's cold outside, sort of thing. If you open a little bit also, the carbon monoxide is not going to go away that easily. It'll stay in that place. So yeah, running a car in a closed garage is a terrible idea. Very bad idea. And if you're sitting inside the car and then running the car, you'll feel sleepy. You'll say, let me take some rest. Because there is hardly any ventilation there. So it'll just do exactly what they did. All right, that is convection. So convection is something that happens in many places, especially in your house. We take care of the convection. We take care of the conduction. Now, what is radiation? Radiation is heat coming out from a hot body. Now, what do you consider as hot body? Anything that is above 0 Kelvin. Anything that is above 0 Kelvin has some activity going on. And that activity is going to be creating what is known as radiation. So energy is going to be radiated out at the speed of light. So this is what we call as a black body. So if I have a perfect black body, I'll tell you what is a perfect black body. A perfect black body is something that is going to emit 100% of what it has and also absorb 100% of what is coming to it. So radiation is going to take place, and the amount of energy that's going to go out from a hot body depends on what factors. The amount of radiation that's going to go, so the delta Q over delta T is proportional to what factors? What factors do you think is?
Temperature.
It simply depends on the temperature only. It depends on, does not matter what temperature the room is in. Radiation is directly proportional to temperature raised to the power of 4. It is temperature raised to the power of 4. That's a different, branch where you learn those things. So temperature to the power of 4, that is where the rate of heat flow is going to be. And what else is it proportional to? Huh? The material, no. I mean, if it's a black body, it's 100% emitter. So it's not the material. Like I told you, this is the most efficient. A black body is something that emits 100%, absorbs 100%. Okay? It depends on area. The more the area of the black body or the surface, it's going to give out more energy per unit time. Putting this together, delta Q over delta T is equal to sigma A T to the power of 4. The sigma is called Stefan's constant. Sometimes it's called Stefan-Boltzmann's constant. S-T-E-F, only one F. Stefan's constant or Stefan-Boltzmann's constant, because it's named after Boltzmann. And the Stefan's constant is a fixed value. As you can see here, okay, the value is 5 that will be given to you. 5.67 times 10 power negative 8. The unit of Stefan's constant is watt, meter square, and then this is Kelvin to the power of -4. And remember, this one should be in Kelvin. This T must be in Kelvin. You're not talking about temperature difference, you're talking about temperature. So only at absolute zero, it will stop radiating. So even if it is at 10 Kelvin, it's radiating. Higher the temperature, higher. You can see this temperature to the power of 4. So the rate at which heat is going to be emitted depends purely on the temperature to the power of 4. Make sense? So for a black body, this is the equation. And this is a fixed number, not for material. It is for a black body, it is this. Now, for other objects, if I'm going to heat something, like me, personally, am I radiating heat? Yes. And the radiation that's going to come out from me is equal to E sigma A T to the power of 4. Now that E is called the emissivity. E is called emissivity. I think it is just written as E. Yeah. It is just E. Some books write epsilon. Emissivity. Emissivity means how good an emitter it is. It's always a fraction. Emissivity is always a fraction between 0 and 1. So when you say E is 0, that means it's the worst emitter. It doesn't emit anything. That's what it means. 1 is a black body. Okay? This is for a black body. So normally, for example, me, I'm not a 100% emitter. So maybe my value will be like 0.3, 0.4, whatever. So am I radiating heat? How much heat is coming out? You can just find out by using this equation. E, which is 0.3, 0.4. Stefan's constant. Area, my body surface, oh, this is surface area. Okay? surface area, and temperature. Now, have you seen the radiators in the car? What color is it? Radiators of a car. It is black. Black is a better emitter. White is a poor emitter. In terms of colors, black is a good emitter. So if both the books are at the same temperature, this will emit more heat radiation than this. You understand? At the same time, black is a good absorber. White is a poor absorber. Understand this? Now, if you have black shingles on your house, when sun hits it, it pulls in a lot more heat and traps it inside. If you use white shingles or white or lighter shade shingles, it bounces from there. It's not everything is absorbed. Not everything is absorbed. Now, if you wondered why Arab men wear white dresses, white headgear, all white, you don't see them wearing black. Because if they wear black, they'll be steaming inside. Because they're walking out in the sun, in the deserts. If you're walking in the deserts with a black dress on, you'll be absorbing a lot and trapping inside. Whereas if you're wearing white, it bounces off. You understand what I'm saying? So white is, so you can write it somewhere. White is a bad absorber and a bad emitter. Shiny objects, basically shiny or white. Shiny or white objects are bad emitters and bad absorbers. So radiators in your car, do you see the area factor there in the radiator? There's a lot of fins. Why fins? To increase the surface area. If you increase surface area, it actually emits out radiation more efficiently. You understand that? And if it is black, excellent. So the temperature is whatever temperature it has, but the emitter, the radiation that's coming out from it, the loss of energy from a hot object depends purely on those factors. If you look at this one, that's a computer. This is a RAM, processors. You can see this. Look at this. There's a chip right underneath, and this is yeah, you can see how the area is increased here tremendously. And look at this one. Where it is sitting is the processor. Now, to make sure that the heat is taken out from there and dispersed, they have these fins. By making that way, it actually is increasing the surface area tremendously. And if it's painted black, it'll be wonderful still. So yes, there are fans to drive that heat out, but if it is just a big chunk of metal, it's not going to do the purpose properly. Why? Because of area. Area. That's why you can see over here the area is increased tremendously by just making it like that. Yeah, so for radiation, this is the equation. Now what is happening right now in this room? What is happening right now in this room? That is me. I am at a temperature T2. And this is a room that is a temperature T1. Okay? So am I emitting radiations? Yes? I'm emitting radiations. Am I absorbing radiations from the room? but the room's temperature is lower than my body temperature. I'm 98.6 Fahrenheit. Room is like 70 Fahrenheit. So definitely, the amount of energy that is coming into me is less. The amount of energy that's going out from me is more. So what is the overall energy that is lost from me? It depends on emissivity. It depends on that. It depends on that. And then, of course, it depends on T2 to the power of 4 minus T1 to the power of 4. This is just the difference between the two. So this one emits according to this equation, and it is absorbing according to this equation. So when you put both together, it's basically this. This is the overall rate at which I'm losing heat to the surroundings by radiation only. Only by radiation. This is the equation for. So if I keep a hot object in this room, this is the equation for it. Because even if it is a hot object, it is in a surrounding. So if you put a hot object, this is a surrounding temperature, and that's a hot object at a different temperature. So this hot object is going to lose heat. Is it absorbing heat? Yes, it's also absorbing heat. But it's going to kick out more heat by radiation than what is absorbing. But ultimately what will happen after a long time, what will happen? Both the temperatures will be equal. When both the temperatures are equal, this will be sending out and receiving at the same rate. So this will be sending out radiation and receiving radiation at equal rates. It will be sending out radiations depending on its temperature. It will be receiving radiations depending on the temperature of surroundings, but the overall heat loss is zero because the temperatures are equal. Yeah. Question? So you understand about radiations? Sun. The temperature of the sun is 6,000 Kelvin. And look at the surface area of the sun. So it is a black body, which means it's one. It is a black body. That means it is radiating out everything it has. Coal is a black body. Coal. When a coal starts burning, do you see anything about the coal at all? Do you see coal at all? You just see light coming out. What light are you seeing? It is just radiation. Just radiation. And because radiation is 100%, you don't see any details of the coal at all. It will be like white. It's because it is 100% emitter. So a black coal is actually 100% emitter. Yeah, heat radiations. So yeah, learn the concepts of these things. More importantly, it's just the concepts. These days in AP testing and all that, the numericals are kind of on the lower side. I'm pretty sure AP Physics B was far better that way because it was touching up on each of these things even numerically. All right, let's move on to the next and the last area, which is laws of thermodynamics. Laws of thermodynamics. We'll give it a start and then we'll continue. There are three laws in thermodynamics. There are three laws in thermodynamics. And this one is called the first law. Okay? And this is called the second law. Am I missing on counts? This is called the first law. The second of the three laws is called the first law. And the third of the three laws is called the second law. What is this called?
Fourth.
I don't know if there's an E there. Yeah, zeroth law.
Why? What?
Yeah, it's called the zeroth law because initially when they listed the laws, they defined the first law, they defined the second law, and then they thought, oh, there must have been a very preliminary, very basic law that should have been stated before this. But already they had called these laws. You know, they called it first law and they called it second law. And how can you write a third law, which is a very, very basic one? And that's why they could not renumber it, and they had to call it zeroth law. Because by the time this came up, these were already into scientific journals and all that as first law and second law. They can't just undo everything. So they had to call it zeroth law. So yeah, it's a funny order. 0, 1, and 2. These are three laws of thermodynamics. We're going to, this is a very simple law that we will do. First law of thermodynamics is what we will do. Second law, we are not going to be into it. Okay? So we'll learn it in next class.